In this video, we're going to continue talking about momentum, and we're going to learn about elastic versus inelastic collisions. So many of our momentum problems look like a collision between two objects. So the simplest example of this that we will see multiple times is, we have two carts on a surface and they have some initial velocities towards each other, or this one could be moving to the right and this one could be stopped. There are lots of different combinations we can have. And then some amount of time later, the two of them collide. So there's some interaction between them. They hit each other, whatever that hit looks like. And then sometime after that, they do something else. Maybe they stick together and stay stuck together. Maybe they bounce off of each other. But this process is a collision between these two objects. So this is the simplest example. We will see other examples of like bats hitting balls and people sliding on the ice and running into each other, things like that. But they all kind of fit into this framework. Okay, so for these collisions, the examples we've done so far in this class conserve momentum, but they did not conserve energy. And we can see that because if we go in and calculate how much energy we have at the beginning and how much energy we have at the end, we don't get the same amount. We have less energy at the end than we did at the beginning, and that's because some energy is being lost during this interaction between the objects. This doesn't have to be the case, though. We can have a collision where energy is conserved, and this is a special kind of collision. This is called an elastic collision. So an elastic collision is one where energy is conserved. And for this to be true, we know that, ignoring this, for energy to be conserved, all of our forces have to be conservative forces. We can't have any friction-y forces. So for this to be true, there has to be no friction or other non-conservative forces. And in the case of this collision where we have two objects hitting each other, in particular, this means that the interaction between the two objects has to be a conservative force. I mean, that's just, that's another way of saying that there are no non-conservative forces. That means the forces that we do have to be conservative. So, for example, this could be two carts that are going towards each other, and the thing that does the pushing on them is a little spring. So if this car has a little spring that this cart runs into and compresses, whatever force between those carts, that is going to compress the spring and store some energy. And we know from chapter 7, energy conservation, that we're going to get all of that energy back, right? If there's no friction or forces like that, we're going to get all of that energy back. So this would be an example of what an elastic collision would look like. There are other examples of forces that conserve energy. One example we use in lab is if the carts have little magnets that repel each other. Magnetic repulsion is for our purposes, it is a conservative force. It's not perfectly, probably, if you really dig down into the details, but it's pretty darn close. All right, so inelastic collisions, on the contrary, energy is lost, and this is due to whatever this force of interaction is between our two objects. So in the case of our two carts, if these two run into each other, maybe the way we do this in lab, actually, one way we do this in lab is to have little Velcro on these two. So the two pieces of Velcro stick together, and in the process, these little pieces of Velcro are soft and kind of squishy, and so it takes some work to push these together, but it's not like a spring. You don't get that work back when you pull them apart, right? The Velcro doesn't push them apart. So that's that's one way you can lose energy. But there are lots of kind of clues that energy might be being lost in a collision. So clues that energy is lost include things like noise. If two objects colliding makes a lot of noise, that is a loss of energy. And probably if something's crashing loud enough to make a lot of noise, it's probably losing energy other ways also. One other big clue is we'll say bending of material that doesn't bounce back. So in other words, if we were talking about a collision between two actual cars, when two cars collide, there's a lot of metal that gets bent, right? And that metal, two cars collide, they get bent, the hood's all bent up. And when you pull the cars apart, they don't spring back to normal, right? This is kind of a, I don't want to say permanent because you could imagine bending it up, but it certainly doesn't bounce back for free the way a spring might, between two objects. So that bending of material takes energy. You don't get that energy back. So that is another clue that a collision is inelastic. Lastly, and this is one that we will definitely see in lab, if two objects stick together. So this is the case in the Velcro one we use in lab. When two things stick together, that is definitely a clue that it is an inelastic collision. That energy is being lost in that collision. All right, so in general, most of the collisions we will see are going to be inelastic. We will only know that they are elastic if we are told this is an elastic collision, or we are specifically told that the force between the two things colliding is happening because of a spring or because of two perfectly repelling magnets or something like that. I think if I was going to give you a problem, it would be a spring. So that would be your clue about an elastic collision. Otherwise, you cannot assume it's elastic, and you should operate assuming it is inelastic and energy is going to be lost. All right. So let's see an example of what an elastic collision looks like and what a elastic collision problem would look like. While I'm erasing, I should say that for inelastic collisions between two objects, we have two objects. If we know the masses of those objects, that leaves us with four different variables, right? The initial velocity of each of the carts and the final velocity of each of the carts, right? So V1 initial, V2 initial, V1 final, V2 final. So inelastic collisions we can solve if we know any three of those velocities. So the examples we've seen, I think we're all, we know both of the initial velocities, and then we know one of the final velocities we want to solve for the other final velocity. So that's how things have to look for inelastic collisions. For elastic collisions, this energy conservation that happens puts another constraint on the problem. What that means is the fact that it is elastic is giving us information that's kind of forcing one of the velocities to be a particular value. And the result of that is that for elastic collisions, we only need to know two of the velocities. So if we know two of the velocities and that it's an elastic collision, we can solve for the other two velocities. And that's what we're going to do next. So I just wanted to prep you for that. So here's our elastic collision example. So let's say we have two carts, and let's see, this one has a mass of 1 kilogram, this one has a mass of 2 kilograms, and this one has an initial velocity of 10 meters per second. And the second cart here is starting at rest, but it has a spring attached to it. So this is a perfect spring, meaning that it is not going to lose any energy, which means this is, of course, an elastic collision. Okay, so we know these two initial velocities. We want to know what are the two final velocities. Okay, so if we were solving this like a momentum problem, we could write down the initial momentum and write down the final momentum and set those two things equal to each other. I'm not going to check to show you that momentum is conserved. Hopefully you believe that for two carts on a frictionless surface, I guess I should say frictionless surface, hopefully you believe that for two carts on a frictionless surface, that is a problem we can solve with momentum conservation because there are no net external forces on the carts. Okay, before we do the equations, I will draw like what the final picture of this looks like. So in between, there is some, the spring is compressed in there. We don't know what's going on. And then some amount of time later, we have our two carts, and we can say, okay, this is V2, this is V1. We want to know what these two final velocities are. All right, great. So our momentum at the beginning is equal to the momentum of cart. I should label these carts just so we can talk about them. The momentum of cart 1, which is mv, plus the momentum of cart 2, which is mv. So that's 1 times 10 plus 2 times 0. That is 10 kilogram meters per second. And that is in the positive to the right direction. The momentum at the end here, of course, we don't know the variables, but we can at least say it's 1 kilogram times V1 plus 2 kilograms. It's number 2, but it's also 2 kilograms. 2 kilograms times V2. Okay, so if momentum is conserved, my initial momentum has to equal my final momentum. So these two things have to be equal, and I'm going to write that over here. And that is 10 kilogram meters per second equals 1 kilogram times V1 plus 2 kilograms times V2. And for the rest of this, I'm going to drop the units. So we'll just 10 and 1 and 2. All right, so this equation is totally correct, but as it is, not solvable, right? We have two unknowns. We could solve for V1 in terms of V2 or for V2 in terms of V1, but by itself, this does not give us a number for either one of those variables. So we need more information. If this was an other momentum problem, if we knew one of V1 or V2, if we had this picture and it said, oh, V2 is 4 meters per second, then we could just plug that in up here and solve for V1, right? But we can't do that because we're not given those. So we need some other piece of information, and that is the fact that this is elastic. So I'm gonna separate that off. So our energy in this problem, we can account for pretty easily. At the beginning, our kinetic energy of car 1 is 1/2 times m, 1 kilogram, times v squared, 10 squared. So that is 50 joules of kinetic energy. The kinetic energy of car 2 is 1/2 m v squared, is just 0 joules. It's not moving. So our total kinetic energy at the beginning, K initial total, we'll say, is equal to 50 joules. All right, what is our kinetic energy at the end? Well, again, we don't know, but we can write it in terms of V1 and V2. So K1 is equal to 1/2 times 1 kilogram times V1 squared. K2 is equal to 1/2 m, 2 kilograms, times V2 squared. So if this is elastic and our energy is conserved, that means this has to equal this. This has to equal these two added together, the total kinetic energy, which gives us another equation. 50 is equal to 1/2 times 1 is just 1/2. So I'm going to simplify this a little bit. 1/2 V1 squared plus 1 half times 2 is 1 v2 squared. Okay, so now we're into, I don't know, advanced algebra land or, some math class. Anyway, so now we have two equations. I'm going to rearrange this top one just so it's a little neater. So we have two equations, 10 equals v1 plus 2v2, and 50 equals 1 half v1 squared plus v2 squared. This now has enough information to solve for v1 and v2, right? This is what we call a system of equations with two unknowns. So two equations and two unknowns, which means that we can, in principle, solve this for v1 and v2. I am not going to make you solve systems of equations like this in class. I do expect you to be able to use momentum conservation to get an equation like this, use energy conservation to get an equation like this, and so I think it's reasonable to expect you guys to be able to write down these equations, but I'm not going to make you solve this system of equations on an exam. In fact, I'm not even going to solve it right now. I'm going to tell you how to solve it, and then I'm going to give you the solution. So to solve this, we can take this first equation, solve it for v1 or v2 in terms of the other one. So say v1 is equal to 10 minus 2v2, right? And then we can plug that into this equation. And so we substitute in for v1 in terms of v2, which leaves us with this equation now that has just v2s in it. And that's something we can solve for v2. And then once we have v2, we can plug that back in here to get v1. Anyway, so that's how you would solve this. When we do that, and you can do that on your own and check, when we do that, we get the following solution. v1 is equal to minus 3.33 meters per second, and v2 is equal to 6.67 meters per second. So if we know the initial state of our carts, and we know that it's elastic, we don't have to know how fast either of them are going at the end. There only is one solution that conserves both momentum and energy, and that is the result that we got. We can plug these numbers back in and show that this solution satisfies our first momentum conservation equation, and it satisfies our second energy conservation equation. We're not going to worry about that now, but if you want to check, you can see that this solution does have the same amount of momentum and the same amount of energy that it's supposed to. So anyway, elastic collisions are important. Like I said, I wouldn't make you solve the system of equations, but I think understanding all the steps in this is important, and definitely being able to, if you have these velocities, could you show that they both did conserve energy and momentum? I think that's a important place to get to. The last thing I'm going to say about this example is we kind of skipped over this middle step here, right? At some point, our spring is compressed and there's energy stored in the spring, and doesn't that matter? Don't we have to worry about the energy, what's going on at this point? And the answer is no. Just like in our other energy conservation problems, if energy is conserved, the only things we really have to care about are the beginning and the end, as long as we can identify where all of the energy is. So whatever was happening with the spring didn't matter at all. The in-between doesn't affect the beginning or the end, because we know enough to write down these equations, and these equations are all we need to get the system of equations that we can solve. So the middle does not matter. Yeah.